Okay, so today I'm delighted to welcome Audrey Schillings, who's an international postdoc affiliated with the University of Leicester, Umeå University in Sweden, and DTU Space in Denmark. And today Audrey's going to be talking a bit about her work that she's been doing during her time here in Leicester. And the topic of her seminar is to do with strong variations in the Earth's magnetic field, which are possibly associated with SAPS. So whenever you're ready, Audrey, I'd like to start. And we'll have time for questions at the end, sorry. Thank you.
Okay, thank you. So, well, I would like to thank you for inviting me first. And today I just realized I didn't put my name on the first slide, but anyway, so as Rosie said, I'm Audrey Schillings. And I would like to talk about first part, which is strong variation in the Earth's magnetic field, and then I will go to the second part, the SAPS. So if you don't understand all of this word yet, hopefully after the presentation, you will know what it is about. So first, so I'm basically working in space weather. So this is the general picture from ESA. And I'm looking at, so in space weather, you have different parts. And you have also, so here you have the sun with a lot of eruption, etc., and then it can do different things to the satellites, and then it can arrive to the Earth and to the ground, and then it can cause problem in our infrastructure and problem. So I'm looking basically at aurora and other atmospheric effects, which are shown over here, and then also in enhanced ionospheric current and disturbances. So basically, we are not in the engineering part of the space weather. So just if some students are joining, I just would like to have a very brief introduction about geomagnetic storm and what are the solar eruption causing to the Earth's magnetosphere and environment. So on the top part, you have in this picture, you have some schematic about the sun and what solar and flares and eruption can do in the Earth's environment. So you have the Earth over here, and then you have the magnetic field. And the sun is then releasing a lot of particles called solar wind, and then they will interact with the magnetic field and the magnetosphere. And so when these solar eruptions are reaching the Earth, they can provoke a compression of the magnetosphere and the disturbances in the Earth's environment. So in this basically two pictures, which are the same, so they represent the Earth's magnetosphere. So you have the Earth over here, you have some boundaries. So here you have the magnetopoles, and then you have the bow shock. Solar wind is over here, and then you have the sun. And so this is represented when it's basically what we call the quiet time, which means that it's normal solar wind activity, no solar flare, no strong disturbances in the system. But then when we have a lot of particles coming in and solar eruption that are reaching the environment, then basically all of these boundaries are compressed and they are pushed towards Earth. So you have still Earth here, and then I represented the magnetopoles a little bit closer to the Earth, and then the bow shock as well. And so that's what we call the geomagnetic storms. So the whole system is disturbed. Then I would like to briefly introduce this very nice schematics from Steve Milan from his paper in 2017. So with the Earth's current system in the polar region. So basically on these two pictures, you have the current system. The magnetopole is the Chapman-Ferraro current. And I would like to strengthen your attention here to the substance current wedge. So this little two blue current. And then on the field aligned current, we are called region 1 and region 2. And then on this schematic, we have the magnetic field line. So basically the Earth's magnetic field or the magnetosphere is closed, which are the blue line. And then we also have some open field lines, which are in red in this picture. And then going from this picture, we can go to the top view of from the pole for the current system. So you have the sun over here. So this is basically illuminated in the day side. On this side, you have the night side. And this picture is quite complicated, but really briefly, if you want more detail, I refer to the paper from Steve Milan here in 2017. So basically, what I want to draw your attention to is the field line current, so the region 2 here and the region 1 over here, because I will talk about that later in the talk, and then the Westward electrojet, which is over here. I'm sorry. So here, the Westward electrojet represented orange, and then the Substorm current wedge, which are basically around midnight for magnetic local time. I will try to get the pointer so it will be easier. Yes, so here you have midtide and the Substorm current wedge, which are also represented here with the current. So then the first part, strong variation in the Earth's magnetic field, so DBDT spikes. So basically, how do? We look at magnetometer network, which are basically instruments installed on the ground at Earth around the world. So here on the right, you have the whole picture from the SuperMAG network, which is a worldwide coverage. And this network is actually taking is more a database actually than a network. So it's taking all the data from other network. And so those data have baselines taking off. So it's very convenient to use. And then on the left, you have two other more local networks. So the image network for Scandinavia over here. And then the new and extended Scandinavia network, which is called Max Sweden project, which is basically a joint project between Sweden and Denmark. And so they have upgraded magnetometer, and they have added magnetometer that will be integrated to the image network. So those are the data I'm using for the magnetic field. So first of all, we started with statistic study for finding DBDT spikes during storm. So how did we do? We took a list that was created by Maria Wallace from her algorithm. In this list, we took all the storm that had the CMH index below minus 100 nanotesla, and then according to this storm, we went to the magnetic data, so to the SuperMAG, and we took all those storms for 1 minute data, because if we took 1 second data, it's way too much space, and it takes too long to download. And this study was for 40 years also. So then we had two thresholds for our spikes. So the variation in the magnetic field, so between 500 and 1000 nanotesla per minute, and then the extreme spikes that were over 1000 nanotesla. And we divided the spikes that we found in 3 categories, because you always have to look at the data more carefully. So we divided them in good data, before and after data gap, and then the one that we didn't think that might be true. So what we found with those statistics and spots and DBDT spikes during the storm, we basically found 2 hotspots. So one in the evening and one in the morning. And so here first we divided so we didn't use the horizontal component in the DBDT, but we divided into the actual component, so the northward and the eastward component. So that's why here you have the DBDT for the northern component, and then the DBDT for the eastern component. And so we basically found 2 hotspots for the northern component, so in the evening and in the morning. So here is represented over here, so it's highlighted by the color. So this tells you how many spikes do you have. And then for the eastern component, we found 1 hotspot only in the morning. And then, so this is for, as I said, global coverage. And then we made distinction between the north and the eastern component, because these hotspots already have been found more locally in other studies. So this was not completely a new result, but what we added was as I said, the global coverage, and then we didn't take the usual horizontal component, but we did found that, for example, there is a difference in the north and the east component. So that was the main result. So then we thought, okay, but now we have spikes. So what are the physical components associated to them? So first of all, we looked for the Substorm current wedge and the Westward traveling surge. So the Substorm current wedge is basically created by a plasma flow that is entering the magnetotail plasma sheet. And then you have an enhancement, and then the signature in the polar ionosphere is enhanced westward electrojet. So here I put you again this nice sketch when you have with all the current system. And so the westward electrojet, if you remember, was over here. So basically you have an enhancement of this orange current, sorry. And so this is what is called the Substorm current wedge. Of course, it's much more complicated than that. So there are entire review and entire paper on those phenomena, but I will not go into all of the details here. So that's what you have to know. And then in this Substorm current wedge, you can also find what is called a westward traveling surge, which is basically an extension of this little part here that will what we call travel in the west direction. And then you have an additional current system that is made in top of the origin one, and that's what is shown here in red. And so this schematic is taken from the review of Kepko et al. In 2019. And so on this middle picture, you can actually see, so UK is over here, Scandinavia is over here, then you have Greenland, and then we can see from the DMSP satellites that they have observed a Substorm current wedge. So also you have to know that the westward traveling surge is not always seen. So it can be there, but it can also not be there. And so we think that this Substorm current wedge and westward traveling surge is actually associated with our evening spikes. So then the other phenomena that we thought that we think is probably related to the spikes is the omega bands. So what are the omega bands? So those are basically instabilities, current instability that are drifting towards the east. So in this schematic, you have again, so all of these always represent the field line current. And this one represents the westward electrojet. And so basically this structure is drifting in the opposite direction, so towards the east. And so it's called omega band because it has the shape of an inverted omega. That's why it's called omega bands. And then for the omega bands, there are a few studies. So there are Partinis et al. They did a full review with statistics about the omega bands. And then it's also Apatenkov et al. So they found that they related all the omega bands they found to DBDT spikes. So this is actually known that DBDT spikes, are actually related to omega bands. And so here you have an example of his paper, so Apatenkov et al. In 2019, of omega bands with also DMSP satellites in June 2003. And so we believe that omega bands are related to the morning sector. So here you have a summary picture of our statistics. So on the top one, you have the northern component. On the bottom one, you have the eastern component for the DBDT spikes. So in the northward component, you can see evening and morning sector here highlighted by the yellow color. And then the morning sector, the morning hotspot, in the eastern component. And then so we believe that the morning spikes are related to omega bands that I just explained, so here, and then that the evening spikes are related to the Substorm current wedge and the westward traveling surge. So then we went from these statistics, and of course we had a lot of storms there. So by playing with the data, we also found some interesting event and particular feature in individual storm, and one of them is the St. Patrick's storm. Oh no, sorry, I'm going too fast. So from this paper, from the statistic, we also found the spatio-temporal sequence. So it means that we took out from our 307 storm, we took out all the storms that had more than 10 spikes. And so here it's a very nice example from, and also very extreme example, the Halloween storm in 2003. So now I'm only talking for the northern components, so the dB and dt. And we found that the spikes, if we looked at the spikes in towards time, so on the y-axis here, you have the magnetic local time, and on the x-axis, you have time. This line shows you the arrival of the CME, so the shock arriving at the CME at Earth, and then after that, all the spikes from the storms. So here you have some, when I mean all the spikes, is like northern and southern hemisphere included, and the extreme and moderate spike that I introduced at the beginning of the talk. And what we found is that the spikes are actually evolving from the evening sector, which is over here, towards the morning sector in MLT. And this is faster than the rotation of the Earth, so it's not due to the rotation of the Earth. It's actually the spikes are seems to be moving from one sector to another. And so here in this event, we found two sequences, for example, here and this other one. It's not depending on the magnetic local latitude or of the geographical latitude either. And it could be related to some bursts in the AU or AL index. So here you have, if we zoom in this lot of spikes at the beginning, we can find others. So here is the zoom, so it's about an hour right after the CME arrival at Earth. And then we can see that we have this huge and massive sequence that are basically spikes moving from, in this case, late afternoon towards even almost noon. So it seems that for extreme storm, it can also not from evening to morning, but also from late afternoon to pre-noon, for example. And we have found this sequence in several of the 27 storms. And I will come back to that as well. So now from there, I want to go to the single event from the single storm that we found and we studied. So we have basically studied the same. So we look for DBDT spikes, but in this case, I don't show you the DBDT, but I only show you the northern component of the magnetic field towards time. And we can see for this particular storm, which is on March 17, 2005, we basically have within half an hour, we have three big spikes in Scandinavia that are very localized. So for this study, we use the image network, which is the Scandinavian network and has 10-second resolution data. And we found that few of stations did see the spikes. So in this example, in the first one, you can see that 3 of the stations have seen spikes, and then a few kilometers away, you can see that 4 others doesn't see the spikes at all. So we were really interested in this. And then we can see that there are basically 3 consecutive spikes, that are next to each other, and different stations are seeing it. So it's not always the same station that are seeing it. So for example, the last one, so the third spikes, is only Abisko, which is this station that is seeing it, while in this case, it's the Luxembourg station that sees the first and the second spike. So we thought that was really interesting. And also we found that these spikes, because the stations are ordered in latitude, the first spike is seen at lower latitude, and then the third spike is seen in higher latitude. So the spike again is kind of moving in latitude, which is kind of interesting. And so for that, we looked at what we call the differential ionospheric current. So basically, you have to know that when you have a magnetic network, you can have, which is measuring the magnetic field on the Earth. If you rotate this magnetic field 90 degrees, you will have approximately the ionospheric current, and that's why it's called the ionospheric current. And so what we do here is that we take different maps, so different time of these ionospheric currents that has been calculated through the magnetic field and through the network, And then we subtract this 2 consecutive time, and in this case it's about 10 seconds. So we subtract these 2 currents, and so we will remove the background current, and we will have only the perturbation of the magnetic field that is left. Of the, not the magnetic field, sorry, of the magnetic field, and then it's transferred to the current in this case. So, and that's what is called the differential ionospheric equivalent current. And so on the left, you have a picture. How does it look like? So in this case, it's taken from the FMI website, so the Finnish Meteorology Institute in Helsinki. And then you can see this is the schematic, what is actually happening. So you have a whole current loop over here, and then to this current loop, you add enhanced Westward electrojet. And then you get this kind of feature when you can see this rotating loop. And so this is also has been described in this literature. And so what we found for the St. Patrick's storm, so it's that we have, for these 3 different spikes, we actually have this, with using the differential equivalent current, we found this system going on and going off. So basically, on this picture, you have the ionospheric current. So the Westward electrojet is representing by the blue color. So you can see there is an enhancement of this Westward electrojet, and they are basically 3 blobs. Then we look in the magnetic field. Okay, we found these 3 spikes. And then when we look at the equivalent current, the differential equivalent current, we could see that, oh, during the first spikes and this first enhancement, we have an on loop. So the system, it has been a perturbation adding to the system. And then this perturbation is basically disappearing in between. So it's the end of the spikes, and it's basically in between here. And then we have another one, and then a third one. So basically, first is on, second is on, third is on, and then off, 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 for these 3 spikes. And this is very localized because it's not observed everywhere in all stations in Scandinavia. And then we could also see that it's actually related to some auroral brightening. Then finally, now we have talked about storm, DBDT spikes during storm, and now we are going for non-stormy spikes. So we have done statistics for non-stormy time, which means that we have found a lot of DBDT spikes when it was no storms, which we do not usually expect them. So on the first plot here on the left, you can see the magnetic field. Again, the 2 component, northward, eastward components for a couple of times. So this is one date, and the station is in Alaska. Then the middle plots show you the DBDT of this component. So DBDT of the northern component and eastward component for the same time, and we can see that there are a few spikes here that are over 100 nanotesla per minute, or even more than 200. And then here you have the 2 magnetic indices to show you about the solar activity, and it's not very strong. So this one was considered as a substorm. But then we also have found spikes where in event where it's not considered as a substorm. So again, here is the same type of plots. So the magnetic field, this is another station though, and another date. But here you have like the magnetic component, the DBDT, and then the magnetic indices. That shows that there is basically, this is the time between 2 substorms. So the yellow are the yellow patches here are what is called a substorm, and then in between 2 substorms, we have interval when we actually found a few spikes as well in the DBDT. And in this case, you can actually see that it's pretty strong because you have like spikes that are going to 300 nanotesla per minute. So there are actually DBDT spikes during storm, but also during non-storm. And that's where we look for that it could be associated with SAPS. So it came from, because usually SAPS are associated with substorm, but it might be that it's not fully known about that. So first of all, what is a SAPS? So a SAPS stands for sub-auroral polarization stream. So, and then the literature about it is enormous. So there are a lot of different things, and it seems that it's not very defined what it is. There are different theory for the mechanism that are producing SAPS. So it's not really well defined. So here I'm based on the review from Nishitani et al. In 2019. And so first of all, I would like to introduce the sub-auroral ion drift. So this is basically around midnight local time. It can be a single or multiple event, and sub-auroral ion drift is basically the ion drift velocity that it enhances and is observed in the F region. Then if you combine to this sub-auroral ion drift, you can have a sub-auroral electric field. So it's basically an electric field that is poleward, and it's associated with some field line currents. But then you also have what is called a polarization jet. So the polarization jets are westward plasma flow that are also driven by polar electric fields. So here comes the first, not confusion, but when it's not that easy to make the difference between the sub-auroral electric field and the polarization jet. And then if you take all of these three and you put it in the sub-auroral region, which is like basically when you have a distant times, you have an enhancement of the plasma convection. And then if you go equal toward of the electron precipitation boundary or the auroral oval, and you put all of these three, you basically end up with what is called nowadays a SAPS, which is a sub-auroral polarization stream. So a SAPS is a combination of a polarization jet or sub-auroral electric field and the sub-auroral ion drift. And so basically characteristic from SAPS is that they are found so below the electron precipitation boundary, so or the auroral oval, and then it's extended in latitude, in longitude, and they have basically a velocity higher than, so it's fast flow, so they have velocity higher than 500 meters per second. But when they say that it's in a region between 60-degree latitude, that's depending on the auroral oval. So actually it could be, if the solar activity is very low and the auroral oval is quite high, forward, then it could be around 62-65-degree latitude. So here you have an example of some SAPS in the SuperDARN data. So this plot is coming from Nishitani et al. 2019. So we have the magnetic latitude in degree over here. Then we have over the time, and the color shows you the velocity. So this event is for the 17th of March 2013 for the beam 4 from one of the SuperDARN radar. And basically the SAPS is that we have this green color here. So this is not extremely high, but it's higher than 500 meter per second. And then here we've made the difference between SAPS and SAID. So the sub-auroral ion drift. The blue part is the sub-auroral ion drift. In my case, I do not make the difference, so I called everything SAPS. So what is that has a velocity higher than 500 meters per second is the SAPS in the data. And so here they are talking about one of the mechanisms that could create SAPS, which are the SAPS wavy structure. So it's basically highly dynamic and localized plasma flow within this sub-auroral ion drift. But as I said, in the literature and especially in this review, you can find different processes that create that could create the sub-auroral polarization stream or the SAPS. So how do you find SAPS? So basically you use this network of radar, which is the SuperDARN radar. So SuperDARN stands for Super Dual Auroral Network. It's a network of HF radar, and they are in both hemispheres. So in this plot here on the left, I only showed you the northern hemisphere with the network. They are working with backscattering signal that are coming from ionospheric irregularities that are aligned with the magnetic field. And then you can, from this backscattering signal, you can get the line of sight velocity from the Doppler shift, basically. And I'm using only the sub-auroral network at this moment. And that's why here it's only the 5 here that are in red. Basically because by definition, the SAPS are in the sub-auroral region, meaning if we consider that the normal auroral oval is around 65° in latitude, all of this radar are below. And that's why I started to look for SAPS in this radar first. But of course, the 2 radar over here could be also used, or a few a bit higher here, probably close to the radar. They might be used as well if the solar activity is not too strong. And so on the right here, you have one of the sites for the radar that I took this picture from the review again from Nishitani et al. And I think it was set up nice because those are the 2 radar I'm actually using. So that was nice to see a picture. So now I will show you some events of SAPS, or basically 2 events from SAPS that I found. So the first one is 14-15 of February 2010. So we looked for this polar plot. In this case, so you have like every plot is about 40 minutes apart. The auroral oval is represented by these 2 lines here. It has been adapted compared to the KP index. So it's based on the KP index. And in this case, the KP index was about 3. So this oval is for KP index 3. So you can see that then the color scale gives you the velocity. The gray is the ground scatter. And so in this case, you can see that basically at the beginning, there's basically nothing. And then there is actually a very high flow in the auroral oval. So this is not a SAPS since it's in the auroral oval. But then this feature is actually moving outside the auroral oval with time. So basically over here, you have SAPS that starts to create because it's not part of the auroral oval anymore. And then you actually found it a little bit later as well in the data. So that's basically a SAPS. So this is for Blackstone radar. It's also seen for the 4th highest east radar. So I do not show the data here because it basically look the same. So I looked for sudden storm commencement. If anything was reported, it was nothing reported about that. This event is basically about 60 minutes, so long. It has fast flow and it's in the sub-auroral region. So it has everything of a SAPS. Then if you look at the line of sight and so line of sight velocity and what is called the range gate. So basically you have the radar over here, which is Blackstone. You have the field of view here, and then each time you have a beam. So in this case, I represent the beam number 8, which is this plot. And so we can see that in this plot, at this range gate, you have basically a very high velocity as well. So this is the SAPS we see previously here, and probably here as well. So then you can see that in different beams, you can see this very high velocity. So beam from basically 5 to 12. Yes, so this was for 14 to 15 of February. Then I also looked for the SuperMAG data. So in this case, it's 1 second resolution because it was only 2 days. So it's easier to download because it's day by day. And so I took most of the station in the field of view of the Blackstone radar. So the radar I just showed you in the SuperDARN. And you have all the magnetic stations that are represented for lowest latitude on the top to higher latitude on in the bottom. And what we can see is that we are, so at the lower latitude, there are not so much variation. So this shows you the 3 components. So the red is northern component, E term is green, and then the Z is in blue. But at higher latitude, we can see that there are perturbations in the magnetic field. So this is basically, this is 14 and 15 of February, midnight is over here. So our time is between these two lines. I didn't show it in the SuperDARN data, but the SAPS is actually re-seen a little bit later in the beginning of the night, in the 15th of February. So this is basically where we see the SAPS, and we actually have some spikes exactly at the same time in the field of view of the radar, which is kind of interesting. So the other interesting thing is that, yeah, the spikes is basically stronger at higher latitude, but the most interesting, and I actually don't know what it is or why, so we have to, I will have to look into that. In the northern component, why you would expect the spikes to be negative, in this case is positive spikes. So that's kind of interesting. And the most interesting thing is that it's seen on the night after. So here it's another example. So it's just the day after. So in the night from 15 to 16 of February 2010. Again, fast flow in the sub-auroral region. This time it's about 1 hour and a half. The KP index is a bit higher, so it might be a substorm. I will come back to that. There is still no thunderstorm commencement reported, and it's also seen in some other radar. So the SAPS are basically over here. So the aurora over is here again. You can see it over here. And so these plots are 4 minutes now. So between here and here, you only have an hour, while before you had a little bit more time. But you can see that for an hour, this SAPS is seen. And then if you go again to same radar, range of gates for beam 10 in this time, so which is about here, you can see the SAPS again, so very high velocity flow. And in the magnetic field, interesting, we see again a positive noseward component in some of the stations. So those are basically the same station as the night before, except one where it was no data. And we see basically the same. So actually here is the first event I showed you. So at the beginning, so 14, and then the beginning of the night from 15 of February. And then here from the night around the same time, same radar, we have the same feature, which I think is very interesting. But this has to be investigated a little bit more and more into details. And then finally, I look at the solar wind data for this event. So I basically took 2 days before the event, so 14 of February, and then 1 day after, so 17 of February. So this is about 6 days solar wind data. So on the top one, you have the total magnetic field, and then the Z component of the magnetic field, velocity, dynamic pressure, and then the some indices, magnetic indices, and then I calculate the epsilon, which I did not put any, any units apparently. I forgot about it. Sorry for that. So basically the epsilon tells you how much energy is introduced by from the solar wind into the magnetosphere. And I highlighted the two parts, so the two events when SAPS are finding the radar in red. So this is basically the first one and the second one. So for the first one, there is some activities going on in the index here, but I don't think that can be called a substorm, because to be a substorm, it's supposed to be AL, supposed to be lower than minus 200 nanotesla, which is not actually the case in this part. Then, but then for the second time, I believe that could be maybe there is a substorm there, but that should be confirmed. So as I said, this is not really sure. But the interesting thing is that so SAPS are usually or I expect to be seen during substorm, which could be the case for this one. But I don't think there is any substorm or very strong activity in this case. So, and that's even more interesting because it means that the spikes, as I showed you before, can be found outside substorm and storm time. And now if SAPS can be also found and associated with spikes, that's even more interesting. So I think there is a lot of things to look at in this database. So that's basically go to my conclusion. So we have looked at strong variation and DBDD spikes, first during storm and even strong or extreme storm like the Halloween. But then we also looked for DBDD spikes during less disturbed time and substorm and non-substorm, or what is qualified as quiet time. And we found in both cases spikes, which can be quite strong. And then our statistics, so about storm and non-storm time, show actually an evolution of the DBDD spikes towards from the evening sector towards the morning sector, which is independent of the solar activity, because this has been shown in both statistics. So during the storm, when I showed you, but also during the other statistics during non-storm time. And this is not due to the Earth's rotation, because we did check that. Then we found some SAPS events that could possibly be related to strong variation. I say possibly because I think there are, first of all, there are only 2 events, so probably there are more events that should be found to be more confirmed. And then also some other parameter might be good to have to confirm that as well. And then it seems that SAPS could actually be found also during non-stormy time. So thank you very much for listening. And I'm very happy to take any question. And if I cannot answer, I'm very happy to take them to me to try to find the answer. So thank you very much.